As promised, I'm going to finish off those examples that I didn't have a chance to get through in class this morning. So let's scroll down here and get to those problems. All right, here we go. So started this one briefly in class, but let's talk about it again. So we want to make this a linearly dependent set. So remember that we want to have non-trivial solutions to the associated homogeneous system that we would form by trying to get a linear combination of these that would give you the zero vector. So in general, when we do that, we make a matrix by writing down the vectors as columns in a matrix. Now, if this is going to have non-trivial solutions, pardon me, then we know that this matrix, since it's square, if it has non-trivial solutions, if we don't get a pivot in every column, that means we also don't get a pivot in every row. So that means in general that if we do the reduced row echelon form of this matrix, we will not get the identity matrix if we're going to have non-trivial solutions to the associated homogeneous system. If it doesn't row reduce to the identity matrix, that means it's not invertible. And another way that we can check if a matrix is not invertible is by taking its determinant and finding out when it's zero. So in this particular problem, we're going to take the determinant of this matrix, set it equal to 0, and solve for lambda. So this is a good chance to review how we do this determinant. So remember that we can do determinants by expansion by minors. This one, there's not really any benefit to any particular row or column. So I'm just going to expand along that first row. So if I expand along the first row, we will have lambda times, oops, let me change that color back again. Let me erase that, there we go. For that first one, we'll have lambda times, and then the associated minor is, remember, we eliminate the row and the column that particular entry is in. It's lambda, 1 lambda. It's also going to be a positive lambda, because remember, we start with a positive here, and then we alternate as we go across and down. So the next one will be a minus 1 times 1 lambda, because that's what we get, 1 lambda, eliminating that row and that column. And then add 1 times 1 lambda, 1. This should look familiar to stuff that we did before break. To get the rest of this, we would have lambda times, this gives me lambda squared minus 1. This is lambda minus a lambda minus 1. And this is a 1 minus lambda. All right, so if we're clever here, we can factor this pretty easily rather than multiplying it all out. This is lambda times lambda plus 1 times lambda minus 1. These are the same thing, right? This is lambda minus 1, and this is minus lambda minus 1 if I factor out a minus. So we've got minus 2 lambda minus 1. Both of them have a lambda minus 1 in them. Factor that out, we're left with lambda times lambda plus 1 minus 2. This part here is lambda squared plus lambda minus 2, which factors as lambda minus 2 and lambda plus 2 and lambda minus 1. So we've got this factored now. So this determinant is 0 precisely when lambda is equal to 1 or negative 2. So those are the values of lambda that make this determinant 0, which then correspond to the values of lambda that make this set linearly dependent. Okay? So again, this is just a matter of taking the determinant. It gives you a nice review of how we take determinants. Here we were just being a little bit clever with our factoring, so I didn't have to multiply that out and then try to refactor. All right, let's look at 13. This says that show that if this set is linearly dependent, then if we add extra vectors to it, it's still linearly dependent. All right, so if we suppose that this set is linearly dependent. Well, what does it mean to be linearly dependent? That means there exist constants, are C1, C2, out to CK. So the constants are real numbers, not all 0, such that when I take C1 V1 plus C2 V2 plus CK VK, we get the 0 vector. All right, so again, we know that these constants are not all 0. So if I take 0 times each of the rest of these, I still get the 0 vector, and I'll have a set of constants that are not all of them are 0. So now we have that C1 V1 plus C2 V2 plus CK VK plus 0 times VK plus 1 plus 0 times VK plus 2 plus 0 times VK plus M is also equal to 0. Again, I didn't add anything here. We know that 0 times the scalar 0 times the vector v gives us the vector 0, and if we add a bunch of 0 vectors to a vector, we still get the same vector we started with. So this didn't change anything. However, we now have a linear combination of the second set of vectors. We have a linear combination of this set of vectors that I'm underlining that gives me the 0 vector, and not all of the constants are 0, because we're already assuming that at least one of these C sub i's up here is not 0. So now we have a linear combination of that second set, the V1, V2, I don't need that brace on there, the V2 ... VK, VK plus 1, ... Lots of writing, I know. VK plus M. That gives the 0 vector. Where at least one of the constants is non-zero. Okay. So again, remember the definition of linearly independent says that they all have to be 0 if we have a linear combination that gives us the 0 vector. So for dependent, it's just at least one. It doesn't matter that all of these were 0. Okay. We have at least one that's not 0 over here. So the whole thing becomes linearly dependent. Sorry, so the set is linearly dependent. All right, let's look at this last one. We didn't get a chance to do this one in class, but this was based on the video that I had you watch before class. All right, so we want to figure out if this is a linearly independent subset of this function space. So again, remember, this just tells me how many derivatives I can take and still leave the derivative continuous. And this says the interval on which the function is continuous and its derivatives are continuous. Sine, cosine, and x sine x are infinitely differentiable at all values of x. So these are members of C infinity. All right, so according to what the last video said, to show that this is a linearly independent set, I need to take the Wronskian of this set and show that the Wronskian is not identically equal to 0. So remember how we get our Wronskian. The first row is just the function. So we have sine x, cosine x, x sine x. The second row is the derivative. So we get cosine x, negative sine x. Here we have to use a product rule, so we'll get sine x plus x cosine x. And now I need to take another derivative, and we do this until we get a square matrix. And so as I had 3 functions to start with, I need to take 2 derivatives to be able to make sure I have 3 rows. This will be negative sine x, negative cosine x, and then This is cosine x, and then when I take the derivative of the first here, I also get a cosine x, so you'll get a 2 cosine x minus x sine x. All right, so this looks like it's going to be fun to do. So again, let's just expand along that first row here. Just for, it doesn't really matter, we don't have zeros to work off of. So we'll have sine x times negative sine x plus x cosine x, negative cosine x, 2 cosine x minus x sine x. Then we get a minus cosine x times cosine x sine x plus x cosine x, negative sine x, and 2 cosine x minus x sine x. And then plus x sine x times cosine x minus sine x minus sine x minus cosine x. All right, so let's see if I can add a page in here. Maybe. Sure. There we go. Nope. Sorry, that wasn't it. Let me see if I can add a page. Somewhere in here I get to add a page. Oh, here we go. Insert a new page. Sorry about that. All right. So going on past that, here we have sine x times, and then we multiply, so we'll have a minus 2 sine x cosine x, and then a plus x sine squared x, and then a minus sine x cosine x, and a minus, oops, nope, sorry. This is going to be a plus, because remember we subtract the product. So we have minus, or excuse me, plus sine x cosine x, and plus x cosine squared x. For the second one, we'll have cosine x times 2 cosine squared x minus x sine x cosine x. And then it'll be a plus sine squared x plus x sine x cosine x. And then the last one is x sine x, and then it'll be minus cosine squared x, and then it'll be minus sine squared x. And remember, with the minus, the diagonal, we've got 3 minuses there, so it'll still be minus. Okay, so this one's pretty easy. So I'll do this one first because it's the easiest one. Factor out a negative, you get sine squared plus cosine squared. So this is negative 1, right? So for that part, we're just left with negative x sine x. That's this part here. All right, let's go back up to this one. These two pieces together give me an x, and this is going to be minus sine x cosine x. So for that one, we're going to have x sine x, because this gives me, remember this part here simplifies to x. So I have x times sine x. That's where that's coming from. And then minus, not 2, minus sine squared x cosine x. So right away we notice something nice is going to happen here. These are going to go away. Not that it matters. We don't want everything to go away. Remember, we're trying to show that this is linearly independent. I don't want 0 at the end. But in this case, those two go away. All right, let's look here. These two now cancel. And if I look at these two pieces together, I get a cosine squared x plus 1. Because I can write this as cosine squared plus cosine squared. So we get cosine squared x plus 1 times the negative cosine. So you get minus cosine cubed x minus cosine x. All right, so now if we look at this, I want to make sure it's not 0. That's the whole point of doing all of this stuff, is making sure it's not actually equal to 0. Okay, so I can factor out a negative cosine. That leaves me with sine squared x plus cosine squared x That's weird. It should not have given me a... Oh, it's plus 1. Never mind. Sorry. It gives me sine squared x plus cosine squared x plus a 1. Sine squared x plus cosine squared x gives me 1. So this simplifies finally to negative 2 cosine x, which is certainly not identically equal to 0. When we use the triple, what looks like a triple equals sign, when we use that triple bar, that means identically equal to 0, or identically equal to something. In this case, if it were identically equal to 0, that means no matter what we plug in for x, we always get out 0. And certainly that's not true for this function. So since the Wronskian of x is not identically equal to 0, meaning again, no matter what you plug in for x, you always get out 0. We see that that original set of functions, sine x, cosine x, and x sine x, is linearly independent. So that's what the Wronskian helps us do, is it helps us determine if a set of functions is linearly independent. So anyway, besides the ugliness maybe of the simplifying here, the process is the same every single time. You put your set of functions in your first row, you keep taking derivatives until you end up with a square matrix. You take the determinant of that matrix and simplify it and show that the answer to the determinant is not always 0. That's the process for using the Wronskian to show something is linearly independent.